Hello everybody, so today we're going to be going over some projectile motion problems, and I'll be showing you how the big five equations, or just the general kinematics equations, apply to such problems. And this will be a new step for most because now we're moving on to motion in two dimensions. As you know, motion can't possibly just happen in one dimension all the time, so this is just a little step up. But with that said, let's get right into it. So for this first problem, it's a ball is thrown from a 10-meter cliff with an initial velocity of 50 meters per second at an angle of 30 degrees above the horizon. And it wants us to find its A, total flight time, B, its total horizontal distance traveled, and C, its maximum height above the ground. So to get started, let's go with A. It's always good to draw out what we want, right? So why don't we draw our little diagram here? And this is going to look something like this. Well, that's not the greatest diagram, huh? So we have our Y component going like this, the total component going like that, and then the X component going something like that, right? So if we want to find total flight time, the only thing that we need to consider is its vertical velocity. So it's v0 or v0 of y. So the initial y velocity. Well, you might be asking, how can we find this? Well, we know its initial total velocity to be 50 meters per second, right? So from here, we can just use our trigonometry to find that v0 of y is equal to 50 meters per second. I'm ignoring the units here for a second. Times sine of the theta, which is the degree angle, right? And conveniently, it's given that it's 30 degrees. So if you know your unit circle, you know this is just going to be 25 meters per second. So that's the first step. But second, we need to apply this to a kinematics equation, right? So the second thing that I want to mention that we do know is that d is equal to negative 10. And now what is d in this case? Well, d is actually our displacement. So from here, if we have our displacement like this, we can use the kinematics equation d equals v0 squared, v0 squared, or v0 times t, plus 1/2 of a t squared. Well, from here, this looks like a jumble of letters, but we actually do know some things. T is what we're looking for, so that's actually pretty good, because that's in a lot of variables here, so we can get that sorted out. We know what d is from right here, so that's actually really helpful, because we do actually know v0 of y. It was given, or not really given, but we found it, right? So, and then we also need to know what a is, but a is just g, because that's the gravitational acceleration, right? So when looking at a projectile motion problem, you just got to split things into the x and y components and then treat it linearly. So really, two dimensions is not more complicated than one dimension. You just have to do it two ways separately. So from here, let's just plug in our numbers. So we get 10 meters equals v0, which was 25 meters per second, times t, plus 1/2 times 10 meters per second squared. I'm using 10 meters per second squared for g here, times t squared. And notice how, since t is going to be in seconds, we can actually just cancel out the seconds in all of these, because this will be seconds squared, right? And that leaves meters for all the units, but that's even more convenient because that means we can cancel out meters as well. Just some dimensional analysis here. So if you simplify this, this is going to give 5t squared minus 10 divided by 2, so that's going to be 2. But let's first deal with this right here. So this is going to be minus 25 t minus 10 equals 0. And obviously we can divide both sides by 5, right? So t squared minus 5t minus 2 equals 0. And if you plug this into your calculator, you're going to get t is approximately 5.37 seconds, just like that. So this is our total flight time to get from this point right here down to somewhere on the floor. All right, so let's move on to part B. All right, so B is asking for how far it will travel on the horizontal, right? So that is asking for our x displacement, our displacement in x direction. And if you remember that this is going to be given by velocity of x times t, which is really convenient because remember, t is equal to 5.37 seconds, as we solved in the first part, right? So if you remember, v of x is always constant. Since we have to neglect air resistance in most of these projectile motion problems in AP Physics 1, v of x will remain constant, which is actually really helpful. So we can find it simply if we just go back to our triangle, right? This is a really bad 30-60-90 triangle, but it's okay. So this is 50 on the hypotenuse. The x value is equal to 50 times cosine of 30 degrees. And this is going to give 25 rad 3, which is equal to, if I do this right, 43.3. And this is obviously in meters per second too. So we can just do some quick multiplying. So d of x is going to be defined as equal to 43.3 meters per second times 5.37 seconds. And this is just going to be equal to 232.5 meters. Oops, almost said seconds. Alright, moving on to part C. So C is asking for how high above the ground will this be? So don't get tricked, because when our motion looks something like this, right, and we find this point, it's very easy to accidentally only find up to here. But really, you need to take into account the plus 10 meters, because it was told that the cliff is 10 meters high. But other than that, it's pretty easy. So recall that v sub v naught of y is equal to 25 meters per second. So this is going straight up 25 meters per second. So we can use our kinematics equation. V of y final squared is equal to v initial y squared minus 2gd, where d is this height up here. So remember to plus 10 at the bottom. So from here, we know that at the very top, Vy equals 0, right? Moving up and down wise, you are not moving up and down at the very top. So this equals 0. But what you might notice is that we can just bring some stuff over. So solving for d gives d is equal to v0y squared over 2g. And we're going to set g equal to 10 meters per second squared, because that just makes life easier. But anyway, this is going to give 625 over 20, which is approximately equal to 3.13 meters. But is that the answer? No, it's not, because we need to add 10 to it. So that's not our final answer. We need to add the 10 to give the final answer of 13.13 meters above the ground. Alright, let's move on to the next question. Alright, for question 2, it's consider the graph below displaying the velocity versus time of a car moving in a straight line track. And here's the given graph. It's a little messy, apologies. But basically what it's just trying to show is that there it goes up in a straight line, comes down in a straight line. And the points that are important are noticed. And those are straight lines like I mentioned. V is going to be in meters per second, T is in seconds. So A, it's asking us to describe what is happening at T equals 1. Well, that's pretty obvious, right? For A, at T equals 1, the car changes direction. Right? Wrong. This is not what happens, because notice, importantly, that this is a velocity versus time graph. So that was wrong. Do not write that. You will miss points. The correct answer is the car begins to slow down. And you know this because speed decreases when v has an opposite sign to a, the acceleration. So when v is opposite of a, it is slowing down. Alright, so for B, it's asking us, what is the displacement of the car, not care, from t equals 0 to t equals 7? Well, as you remember, if you take the area under the curve of a velocity versus time function, you get displacement. So in that first triangle, it might be hard to see, but this intersects at 1, 2, 3, 4 and a half, 4.5, which is also equal just to 9 over 2. So if we take 9 over 2 seconds, actually, does that make sense? No, that doesn't. I apologize that this is very, very badly drawn, but this is taken straight off a AP exam. This should intersect at 5. I apologize for this. This is a very badly drawn diagram on my part, but it intersects at 5. So that area of that first big triangle is equal to 5 times 20 divided by 2, which is going to be equal to 50 meters. But then this small triangle will have a base of 2 times 10 divided by 2, which is going to be 10 meters in the opposite direction. So taking the difference will give us 40 meters like this of total displacement. All right. And then it's asking us, see, where does the car change direction? Like I said, I apologize, this is really badly drawn, but it should be at 5 if you take in the account of these equations and these given points where these must intersect. This will actually give us the car changes direction at t equals 5. All right, moving on. All right, for this last question here, it's if an object is thrown into the air and takes 8 seconds to strike the ground, neglecting air resistance, how fast was the object thrown straight up, and how high did it go? And this type of question seems like there's not enough information, and truthfully, there isn't much information. We know t total is 8, right? And we know that a acceleration equals g, which is equal, we're going to call it 10 meters per second squared. So what can we do here? Well, if you remember, the velocity on the way up, the maximum thrown velocity, will match the maximum velocity on the way down. And what this tells us is the up trip takes the equal amount of time as the down trip. So basically, we can rephrase this as if an object takes 4 seconds to fall to the ground, how high did it fall from, right? So this is actually much easier to figure out, as we know that our displacement is something, right? We want to find out the height, but we know that it is 1/2 a t squared, where t is 4 seconds, and know that a is equal to g, which is 10. So we're going to get d is equal to 1/2 times 10 times 4 squared, which is equal to 8 times 10, which is 80 meters. So that answers the second half, that it goes 80 meters high. Well, now you may be wondering, well, how do we find our velocity, right? Well, remember what I told you. The velocity right before hitting the ground will be the same as the velocity it was thrown at. So we can use our kinematics equation. V final squared is equal to V initial squared plus 2AD. And remember, our V initial is going to be this velocity at the top going to the bottom, because our D is from the top to the bottom, like this. So we can set this V initial squared to 0. So you get V squared is equal to 2, and then we're going to multiply by the G, 10 times our distance, which is 80. And this is going to give us V squared is equal to 1600, like this, where V is equal to 40 meters per second. And yep, that's pretty much it. That's all I have for today. I hope you guys enjoyed watching, and I'll see you guys next time, where we will be finally going over dynamics.